This is the 8th video on Lebesgue integral. So today I am going to explain what is general Lebesgue integral. So now just see what is general Lebesgue integral. Let's suppose f is any real valued function defined on a set E. Then its positive and negative parts are defined as positive part is a max of f comma 0 and negative part is also the max of minus f comma 0. So clearly both these functions are non-negative. Our f positive is non-negative, our f minus is non-negative, right? Because it is a max of these two. So if f is positive, then minus f will become negative. So negative comma 0, the max will be 0. So the maximum, it means our f positive and f negative, both these functions are greater than equals to 0 because these are the max of f and 0 minus f and 0. So it means both these functions are non-negative functions, right? So if we are given any f which is real valued function, we can express this f as the difference of two non-negative functions. Now just see an example. Let's suppose our fx is 1 when x is rational and it is minus 1 whenever x is irrational. Then what will be the f positive part? It is a max of f comma 0. Now, what will be the max of f comma 0? Now just see, whenever your x is rational, the value of function is 1. So for x rational, the value of function is 1. So the max value of 1 comma 0 will be 1. And whenever your x is irrational, the value of the function is minus 1. So the max of minus 1 comma 0 is nothing but the 0. So f positive part attains value 1 for x rational and 0 for irrational. Similarly, f negative. F negative is nothing but the max of minus f comma 0. So now just see, when your x is rational, the max of minus 1 comma 0 is 0. So f minus attains value 0 when your x is rational, and it attains value 1 when your x is irrational. So when you substitute for x to be rational, the value of the function to be minus 1 over here, you will get minus 1 minus times minus 1, which is 1. So max of 1 comma 0 is 1. So f negative part attains value 1 for irrational and 0 for rational, right? So now just see what will be your f. It will be the difference of these two. Now just see, whenever your x is rational, what is the value of f positive? Its value is 1. What is the value of f negative? The value of f negative is 0 in case of x rational. So 1 plus 1 minus 0 gives you 1. So the value of function is 1 for x rational. So when x is irrational, f positive value is 0 and f negative value is 1. So 0 minus 1 is equal to minus 1. So the value of function is minus 1 for x irrational, right? So if you are given any function, you can always express that function as the difference of two non-negative functions. So the max of f comma 0, this is the max of minus f comma 0. One more observation, whenever our f is measurable, then we know that the max of these two function is measurable, max of these two function is measurable. So it means f positive and f negative both are measurable. Vice versa, if our positive and negative, these two parts are measurable, then the difference of two measurable is again measurable, which implies f is also measurable, right? So once again, see, whenever we have any real valued function defined on a set E, its positive and negative parts, they may be defined as this, and f is measurable if and only if its positive as well as negative part both are measurable, right? And what is the value of mod of f? Mod of f is nothing but the sum of these two non-negative parts. Same, in the same example, you can clearly see what will be the value of mod of x. It is 1 always for every real numbers, right? So when you add them, you will get nothing but 1. Now how? Whenever your x is rational, the value of f positive is 1 and f negative is 0. So 1 plus 0 gives you 1. The mod of f की value क्या आ जाएगी? It will be 1 for x to be rational. Whenever your x is irrational, the value of f positive is 0 and f minus is 1. So when you substitute here, its value is 0, its value is 1, so you get the sum is again 1. So mod of f attains value 1 for all real numbers. So mod of f is defined as the sum of these two non-negative functions. So now how to define the integrability? A measurable function f is said to be integrable over any set E if both positive and negative parts are integrable over E. And we can write the integral of f over E as the integral of f positive minus the integral of f negative, because our f is the difference of these two. So integral will be the integral of this minus the integral of this. And how to find out the integral of f positive and f negative, we have already discussed in the previous videos, that how to define the Lebesgue integral of non-negative function. Since both these functions are non-negative, so we can define the integral of these two functions. So the definition says a measurable function f is said to be integrable over the set E if both these functions are integrable. Moreover, the value of this integral will be the integral of this minus the integral of this. Similarly, the integral of mod of f will be the integral of this plus the integral of this. So based on this, we have a theorem that a function is integrable over E if and only if the mod of f is integrable over E. Now this you can prove by yourself. This is very easy just by the definition. Now what is given to us? F is integrable over E. Then clearly both the positive and the negative parts are integrable over E. Right? So it means the integral of f is the integral of f positive minus integral of f negative. Both these are measurable. And what is the value of integral of mod of f? It is the sum of these two. So since this is integrable, the sum of two integrable functions are again integrable. So we get the mod of f is integrable. Now conversely, if mod of f is integrable, if this value is finite, then clearly this is finite, this is finite. So the difference of these two is again finite, which implies f is also integrable over E. So this theorem is very important, which says the relation between f and mod of f. So whenever our f is integrable means the value of integral is finite. It is Lebesgue integral. The Lebesgue integral of this function exists, moreover the value is finite. Then mod of f is also Lebesgue integrable and its value is finite, right? And vice versa, right? So this is a remark that Lebesgue integration is absolute integration, means f is integrable if and only if mod of f is so. In other words, we can say Lebesgue integral integrates only those functions whose absolute value functions are also integrable, but this is not in the case of Riemann integral, right? But this is not in the case of Riemann integral. Now just see how. For example, if we are given a function which is defined on the closed interval 0, 1 to r by, whenever your x is rational it is 1, for irrational it is -1. So clearly mod of f is 1 on the whole interval 0, 1. So it is Riemann integrable because it is a constant function. However, f is not Riemann integrable because in that case your lower sum is not same as that your upper sum, right? So this function is not Riemann integrable. However, mod of f is integrable, and in Lebesgue sense this function is integrable as well as mod of f is also integrable. Now what is the value of Lebesgue integral of this function? It is 1 into the measure of a rational plus -1 into the measure of irrational over the interval 0, 1. So the value of this function, value of the Lebesgue integral of this function will be 1 into 0 plus -1 into 1, so which is -1, right? And mod of f attains value 1 into the measure of this, which is 1, right? So this function is Lebesgue integrable. It mod of f is also Lebesgue integrable. However, in case of Riemann integral, f is not Riemann integrable, but mod of f is Riemann integrable. Now one more example, which in this example we will show that this function is not Lebesgue integrable over the interval 0 to infinity. Now just see what is the function. Our function is defined on the 0 to infinity to r by this. Whenever your x is not 0, the value of the function is sin x by x, and whenever your x is 0, its value is 0. And this example you can show by yourself that this function is improper Riemann integrable. However, it is not Lebesgue integrable over this interval. Now to show that this function is not Lebesgue integrable, it is enough to show that mod of f is not integrable. So for this we consider the integral 0 to infinity mod of sin x by x, and we will prove that this is nothing but infinity. Now for this we consider the integral 0 to n pi mod of sin x by x, and we divide this interval into partition from 0 to pi, then pi to 2 pi, then 2 pi to 3 pi, then 3 pi to 4 pi, and so on. Okay, so we can add all these integrals. We will get the value of integral over 0 to n pi. So 0 to n pi can be written as summation k minus 1 pi to k pi, where k is varying from 1 to n. Right? Now we can apply the transformation. We can substitute x to be z plus k minus 1 times pi. Right? So when you substitute x to be z plus k minus 1 times pi, so whenever your x is varying from k minus 1 times pi, your z is going to 0, and whenever your x is k pi, your z is going to pi. So we make a transformation over here. We substitute x to be z plus k minus 1 times pi. Dx will be replaced with dz, and limits will be changed. Now it varying from 0 to pi. Okay. So now just see, we get this integral. Clearly this integral will be greater than or equal to this integral. Now just see how, since it is divisible by z plus k pi minus pi. So 1 over this number clearly greater than equals to 1 over k pi. As we know that z plus k pi minus pi is less than equal to k pi, so 1 over this number is greater than equals to 1 over k pi. So we replace this number with k pi. So this integral is greater than equals to this integral, right? 1 over pi is constant, we can take outside, it is independent of k. So we get it is a summation of 1 over k integral 0 to pi mod of sine z dz. Now you can find out the value of this integral. The value of this integral is given by, it will be split into 2, from 0 to pi by 2 and from pi by 2 to pi. So what is the value of mod of sine z from 0 to pi by 2? From 0 to pi by 2, the mod of sine z is positive, and from pi by 2 to pi, again it is positive. So you can integrate this. It will minus cos z. When you substitute the limits, it will give you the value 2, right? So you can write down, substitute the value of this integral, it is 2. So we get this is summation k varying from 1 to n 2 upon k pi. So when you take limit n going to infinity, you will get infinity over here, and over here also it is 1 to infinity. So the value of this integral will be greater than equals to the summation k varying from 1 to infinity 2 upon k pi. Now this is the series behaving like series 1 over k, and we know that by p series test that this series is divergent. What the p series test says, it says that whenever you have a series of the form 1 over n to the power p, then this series is convergent if p is strictly greater than 1, and it is divergent when p is less than equals to 1. So this is behaving like the series 1 over k. So by using p series, we get that series is divergent. So it means its value is infinity. You can also use Cauchy integral test over here. So when you integrate 1 over k from 0 to infinity, you will get the value of integral is infinity. Its log n, which is infinity. So the value of this integral is greater than equals to infinity. It means it is nothing but infinity. And since this is infinity, so it means the value of integral of f is also not integrable, because we have done the theorem that a function, a measurable function, is integrable over a set E if and only if mod of f is integrable. So since mod of f is not Lebesgue integrable, so this implies f is also not Lebesgue integrable over the interval 0 to infinity. But you can show by yourself that this function is improper Riemann integrable. You can use the Laplace transform to find out the value of this integral, and its value is pi by 2. So this function is improper Riemann integrable. However, it is not Lebesgue integrable. Thanks.